Alright, today I'm going to be talking about thermodynamic relations, which is sort of a fuzzy topic in thermodynamics because sometimes people just don't teach it very well, or just the topic itself is pretty obscure because you've never seen this kind of problem solving before. So hopefully I'm going to give you guys some clarification and hopefully some methods of solving these kind of problems that will make it much easier for you. The book I'm going to be referencing is Fundamentals of Chemical Engineering Thermodynamics by Dahm and Visco. And I'll let you guys know what problems we're going to be looking at so you can follow along if you want to. So first off, if you've most likely taken multivariable calculus, and you may have seen the total derivative before. This comes up very often because it's usually the first place you start, since the total derivative looks very similar to fundamental property relations. Expansion rule is another useful Calc 3 or multivariable calculus trick. Same thing with the product rule, triple product rule. Also notable is these fundamental identities. These are really just basic mathematics, and they just make sense if you look closely at them. So this is just the reciprocal identity, which says that delta x, delta y with z constant is simply equal to 1 divided by the reciprocal of that. And that's just mathematics. I'm pretty sure you can understand that one. No problem. This one, you have delta x over delta x, which is of course 1. Therefore, this entire term is equal to 1. This one, you have delta x, delta y. However, we have this x here, and this x, of course, indicates that x is constant. So if x is not changing, delta x is 0. 0 divided by anything is 0, so this whole term is 0. These come up very often, and they're really useful to continue with your problem. If you miss it, you're going to have a big problem. We also have fundamental property relations, which is really thermodynamics in a nutshell. We have internal energy related to entropy and specific volume, specific enthalpy related to specific entropy and pressure, and a lot of other things. We have Helmholtz energy and Gibbs free energy, and these are really going to be the first places you start these problems, because of course we're looking for thermodynamic relations, and here they are. So those will come up very often. Over here we just have some definitions of properties that you might want to know. So heat capacity with pressure constant is equal to delta H delta T with P constant. You may know that one already. This one's a little more obscure and may be derived by your professor or not, but this is also equal to temperature times the change in specific entropy divided by the change in temperature with pressure constant. Same thing with CV. So constant volume heat capacity is equal to delta U over delta T with the V constant, but it's also equal to T times the change in entropy divided by change in temperature with a specific volume constant, or volume constant, sorry. So these will come up often as well. Sometimes it's going to be hard to spot them, but if you just look back at your formula sheet, or you just you'll start to recognize them after a while of doing these practice problems, which is a good idea because once you get them down, you get them all down. We also have Maxwell's equations, which also derives from mathematics, and it's just a useful tool to getting to where we have our knowns and we can use them to solve some problems. Alright, we're going to start off with problem 6-8 from the book on page 284, part A. So we want to derive an expression for the delta H, delta T with specific volume constant. And we can have P, V, T, Cp, Cv, and S appear in our expression, but we can't have the change in S appear in our equation. So how we start is we look at our main change. So what we're looking for is the change in enthalpy. So we're going to look at our fundamental property relationships, and we're going to look for enthalpy. So this is the fundamental property, so we're going to start by writing that down. So we have dH is equal to TdS plus V dP. So now we want to start making some relations, and the way we do that is use the total derivative. Again, that's right here. where our x is h, our y is s, and our z is p. So let's do the total derivative. dh is equal to delta h delta s with p constant times ds plus delta h delta p with s constant dp. So now we can notice something. Here we have dh, dh, ds, ds, dp, dp. So we can say that t is equal to this change, and v is equal to this change. So now we have this relation. But what's the significance of this? Well, our next step is to use the expansion rule. But we're going to run into problems if we don't have too much information. So what we did this for is so that we can force these relations to appear in our expansion rule, so we can just replace them with variables that we might know. That is, variables that we are stated that we can use. So let's do the expansion rule. But what's x, y, z, k, and l? Well, let's look at the original problem. Delta h, delta t, with v constant. This is our x, this is our y, this is our z. So what's our k and l? Well, because we want these terms to be forced into our equation, then we're going to make s, k, and p our l. So let's plug it all in. We have delta h, delta t, v, which is what we're solving for, is equal to delta h, delta k, which is of course our s, with L constant, which is our p, times delta s, delta y, with z constants, plus delta h, delta L, which is p, with k constant, which is s, times delta p, delta z, with v constant. Z constant, so that's v. So now we have a situation here where it just looks like a big mess of things we don't even know. What's this? What is that? What is that? What is that? Who knows? Well, we know, because we establish a relationship up here. We know that delta h, delta s, with p constant is t, and we know that delta h, delta p, with s constant is v. This is why we used forced k and l to be s and p, so we can force these to appear here, and we can cancel them out. So, we can rewrite this. Delta h, delta t, with v constant is equal to t times delta s, delta t with v constant, plus v, constant, specific v, times delta p, delta t with v constant. So now we're getting to a point where there's not much left to do, because this problem wants us to put things in terms of these variables and the change of them, except for s. However, this has a change in s, so we want to get rid of this. This is fine because it has everything that's specified. So what we have to do is look at our properties. So t delta s, delta t, with respect to v constant. If we look at our heat capacity, we see that right here. Actually, sorry. right here. So that's actually CV. So we can replace that. So delta H, delta T with V constant is actually equal to CV plus V delta P delta T with V constant. And with that, you're really done with this problem. We've made our expression, and we've met all of our requirements. So, yeah, that's one method of solving these kind of problems. It's pretty much the same for most of the problems, but you'll see that it differs for some of them. So let's just do a rundown of our process. What we did first was use our fundamental property, and then we made the total derivative for that fundamental property in order to establish two relationships. With this, we forced these relationships to appear in our expansion rule. So that was the next step. We did total derivative, then expansion rule, and we forced these two to appear here. From there, we simplified using our other properties, and that's how we got here.